Motor reversing controls. In this presentation, we're going to be looking at terminal numbering on a reversing starter, the basic operation of a reversing starter, and finally, common interlocks that are associated with reversing starters. The terminal numbering of a reversing starter, if it is manufactured in North America as a NEMA style starter, will have a NEMA 1 or terminal 1 to the left of the stop push button, then NEMA 2 and 3 in the forward circuit, and NEMA 4 and 5 in the reversing circuit. If we're working with an IEC reversing starter, the components used to build such an item are identical, meaning that the terminal numbering does not change in any way. 1314 is for the holding contact, A1, A2 is for the actual coil. The basic operation of a forward reversing starter is that we have two separate contactors and one overload relay. Their forward push button will control the forward contactor and the reverse push button controls the reverse contactor. Right now, the motor's running in reverse. If we want to reverse the direction and make it go forward, we have to energize the other contactor. And in doing that, the motor will reverse direction due to the reversal of two line conductors. Two line conductors being reversed to a three-phase motor will cause the stator rotating magnetic field to change direction. There are three different interlocks commonly used in reversing starters: mechanical interlocking, electrical interlocking, and push-button interlocking. Mechanical interlocking is shown with a dotted line and a horizontal solid line that makes contact with two interlocked coils. It is typically a mechanical device that is connected between two separate contactors, and the purpose of it is to prevent the possibility of a line-to-line short circuit in the power circuit due to its teeter-totter or pivot point type of operation. Only one of the armatures will be able to seal in at any given moment. In a system that has no mechanical interlock, while it is running in reverse, an individual could come along and press the start forward button. In this situation, this contactor would then engage and all contacts would reverse directions or reverse states. In this situation, you can follow line 1 here all the way through the contact to this point and now to line 3, which would be a line-to-line short circuit. This one from line 1 or line 3 goes up here to line 1. Again, a line-to-line short circuit. The results of this are catastrophic failure and a pile of rubble. And so the entire motor starter would be destroyed and would pose a significant safety hazard to individuals if they are around that equipment when it went boom. Instead, we use mechanical interlocking to prevent the second coil from actually sealing in the armature and the contacts changing state. It does not prevent the coil from being energized, but rather prevents the articulation or movement of the armature. Electrical interlocks is shown on a schematic diagram as simply electrical normally closed contacts. In this situation, the R coil has an R contact in series with F, and the F coil has an F contact in series with R coil. The reasoning behind this is that if R is energized, this contact will be open and prevent F coil from being energized. The exact same process will take place on the bottom. If F coil is energized, F contact will be open and prevent R coil from being energized. The electrical interlocks are commonly seen as accessory or additional control contacts that are mounted on the contactor itself, and at times are actually mounted inside on the mechanical interlock itself. Again, the purpose of electrical interlock is to prevent damage to the coil if both were energized, but one was prevented from pulling in due to the mechanical interlock. Let's look at a system with no electrical interlocks. It's running in reverse. An individual presses down the forward push button, and we already know that there will be no short circuit due to the mechanical interlock. However, The mechanical interlock prevents the F armature from sealing in, and this causes a relatively high value of current to flow in the F coil. This will then cause significant heat, and it will fail fairly shortly due to the insulation being over temperature. Instead, if we use electrical interlock like this, when the R coil is energized and the motor is running in reverse, the R contact in the forward section will be open. Now, when someone comes along and presses down the push button, there will be no voltage that is applied to the F coil because of the open R contact. And because of this, the F coil is protected from overheating damage. Push button interlock is shown on a schematic diagram as a split 4-terminal push button. It has a dotted line that connects two plungers together, and it represents the operation of them in simultaneous motion, meaning when the top plunger moves down, the bottom plunger moves at exactly the same time. Now, there are not two separate push buttons here. Instead, it is showing a single 4-terminal push button with a single plunger. And we can see that the plunger is either making contact with two terminals at the top, normally closed, or when pressed down, will make contact across the two bottom terminals, which are normally open. Often we will have dual self-contained push buttons where there are two separate contacts already built into the assembly, or we'll have individual normally open contacts and normally closed contacts that we can then place into a push button enclosure like this one. And we can see that when the push button is pressed down, it pushes on these two toggles, and that is what actuates the contacts inside. Push button interlock allows for the motor to be reversed without pressing the stop push button of the circuit. Well, let's see how this would work in a no push button interlock system. Right now it's running in reverse. And if we wanted to have this system immediately go into forward, we could press the start forward push button. So let's give that a try and see what happens. We'll press it in, and of course the F coil does not energize, and that's because of the R electrical interlock in series with it. So instead, we would have to go over to the stop push button, de-energize the entire circuit, and then come back and press down on the forward coil. Or the forward push button energizes the forward coil, and all of the contacts associated with the F coil would then change state. We would have a holding path, and we could release the push button. Now, at times in crane operation or other types of installations, we will want an immediate means of reversing the motor's direction instead of pressing the stop button. In these situations, we need push button interlock. So let's see how this differs in its operation. We want to reverse the direction of the motor's rotation, and we want to go forward direction instead. So we're going to press down the forward push button. Notice that immediately voltage is applied up to the normally open contact. Also, immediately the normally closed opens and de-energizes the reverse coil. Remember, it will take a few microseconds for the R coil to then release its armature and for the contacts that it controls to go back to their normal state. There, now they've gone back to their normal state, and we can see that there is now a connection all the way through to the F coil, allowing for the F direction to now be instituted, a holding path, and we can then release the push button. Push button interlock allows for immediate reversal of motor rotational direction without having to first press the stop push button.